Okay, so here's the last thing with centripetal motion. So here's how this is going to play out. So we got the last of centripetal motion today, being Friday. We'll start deriving gravitational equations and going through all the theory. That'll kind of take Monday and Tuesday of next week. Then we don't have school Wednesday, and then we've got one big massive gravity assignment that'll take us like Thursday and Friday, review on Monday, the test will be the following Tuesday, okay? So that's kind of where we're looking. All right, so up to this point in time, all of our motion has been horizontal like this. Preston, is gravity pulling down on the rubber stopper? Yes, okay? Gravity is pulling down, your centripetal force is acting inward. That's what you've got. But if I take this and swing it in a vertical plane like this, okay? So now I'm going around like this. So here's the question. Assuming that the speed is constant as this thing goes around, when is this strain going to be under maximum load?
At the bottom.
You've got three options. At the bottom, at the side, at the top. Preston, you chimed in early with the bottom. Why?
Because that's when you're going down and gravity's also pulling down. Whereas like at the top, gravity's pulling down, but the stopper's trying to go up.
Okay? Not bad. Not all bad. So here's the story. What if I could swing this thing around, even in a vertical path, and I could shut off gravity? So if in this little zone I could swing it like this and shut off gravity, would there still be tension in the strain?
Yeah.
Yes.
Why?
Because you have centrifugal force.
Yeah, you still have to have the centripetal force to make it move in a circle, right? So no matter what, when this thing is moving in a circle, I have to have a certain amount of centripetal force to keep it moving in a circle. Okay. Now, we're back to gravity, but now we're not going to have any motion. So if I just hold this thing up here, how much tension would be in the strain? Enough to balance out what?
Gravity.
Gravity, the weight of it, right? So if this thing goes around like this, here's what you want to think through. And we're going to look at two extremes. So when this thing is at the bottom of that loop, clearly you have to have some centripetal force, okay? Because it doesn't want to travel in a circle. This thing it wants to travel in a straight line. So you know you have to have, no matter what, you have to have some centripetal force. Now, it's also what Preston said. Gravity is pulling down on that thing as well. So not only do you have to provide the force to change the velocity vector, you also have to provide enough force to overcome that gravitational pull. Now, if you want to call this force normal, if that's what you want to think of it, hey, that's cool. Technically, that's not right, because typically your normal force is provided by like a solid surface. So here's the easiest way to think this through. And I've tried probably 5 different ways over the years. Just realize that the total force at the bottom is going to be the sum of your centripetal force plus your gravitational force. And think of this as just like an absolute value, okay? Now, all of this is on the back side of the lecture notes that I gave you on centripetal motion. So the back side of those lecture notes is devoted nothing other than this vertical motion. So if there's ever kind of a section of notes that you might kind of read through and highlight and actively take notes on, that would be it. So what that means is that when you're at the bottom, you're going to feel heavy. Now, the other extreme is when you're at the top. So when you're at the top of that arc, do you still need centripetal force? Capshawn. Really. I don't need centripetal force to make it move in a circle. At the top, it will magically go around. So let's go with yes. Okay? So I still need a certain amount of centripetal force. But here's the difference. When you're at the top, gravity is working with you. Okay? Gravity is helping in that downward force to help, whereas at the bottom, you're working against it. So if you add these at the bottom, what do you think you're going to do at the top? Force centripetal minus Fg. Okay? That's it. So you all intuitively understand this equation, and I'll show you why. So I'm going to switch over to that laptop so I can show you the video.
Giga roller coaster.
Okay, so what this is like a computer-generated version of like a roller coaster from the point of view of inside the coaster. In that roller coaster, when you are at the bottom of that hill, what are you going to feel? Heavy or light?
Heavy. You feel like your soul's being pressed through
Why?
sphincter. Because you're experiencing a bunch of G's as you go from down to
But
not
what's
down.
creating the G's?
Gravity.
The
Yes, so when you're at the bottom of that,
Oh yeah, because you're like.
if you're at the bottom, okay, if you're at the bottom, when you hit that very bottom, what does your body want to do?
Collapse.
keep moving down.
It wants to keep moving in a straight line, and gravity wants to pull it down. So that track and that seat has to provide two things to you. It has to change the direction of your velocity vector to the inside, and it has to overcome the pull of gravity. Now, this would be weird, but stay with me because it's in the name of science. Let's say that you get on that roller coaster and you happen to have a bathroom scale, okay? And you're just sitting there, it hasn't moved. You put the bathroom scale and you sit down on it and you look down and it's reading 100 pounds, okay? 100 pounds.
Featherweight.
You're not moving, you're sitting there, it's 100 pounds, right? So when you're at the bottom of that ramp, going curved like that, that you just experienced, what do you think is going to happen to the reading on that scale?
It's gonna increase.
It's going to
A lot.
increase. Because again, what's happening is that your body wants to do two things. It wants to get pulled down by gravity, and it wants to move in a straight line. So that scale is reading those additional forces to keep you from falling and to change your direction. top of a hill, what are you gonna feel?
Light.
Right.
You're
Wait.
gonna feel lighter, why? Less gravity? There's
No, because
no way
you
to
want
go.
to keep continuing in a straight line, which in that case is straight up. So you want to fly away.
That's right. Or when you're at the very top, you want to turn into a projectile. You want to turn into a lemming problem.
Yeah.
Yes.
Okay?
Actually, probably more akin to
So,
both, probably.
at the top, instead of reading 100 pounds, it's going to read
Probably 0.
less. Well, if you're
Yeah,
saying
we're gonna
weightlessness, okay?
leave though.
But it's certainly going to read less. It isn't because gravity is weaker, it's because you want to keep going in a straight line, okay? And you basically want to go flying off. So when you're at the top, that's when you subtract the two values. So you take FC minus FG. So because you're subtracting, and we'll talk about this in the next video, because you're subtracting, is it possible for that force total, and the total force is what you experience, do you think that's possible to reach a point of 0?
Yes.
Yes, you would be in a state of
Equilibrium.
weightlessness. You would be floating. It'd be like it's like you're in orbit. So if you take force centripetal minus Fg and you get 0, that means you're in a state of weightlessness. Okay. Light. Heavy. Light. And there we are. Okay.
Yes.
In the early days of space exploration, NASA developed a technique to recreate zero gravity, the notorious vomit comet. Because the weightless effect of microgravity is nothing more than a continuous free fall, it's possible to simulate it by flying an aircraft in a huge arc or parabola, which, for short periods of time, allow those on board to float as though in space. But the stomach-churning ride could spell trouble for some people.
Oh.
All right, I know what you're thinking. I've got this some flight. I'm not gonna get stylish flight suit, including entrepreneur and astronaut Richard. This is one of the only privately funded training facilities, offering the public a rare opportunity to cheat gravity in this specially modified Boeing 727.
Okay, so here's what they're going to do. So if you look at that equation that says force total up at the top, and remember, listen to me, whether you're at the top or if you're at the bottom, that force total, force net, however you want to think of it, that's what you're going to experience. Now, visualize this. If you look at force total equals Fc minus Fg, that's what you're going to experience at the top. If you're going to subtract them, you're going to add them at the bottom. So right now, how much, within the context of this room, how much centripetal force are you all experiencing? None. Okay? You're not. So right now, you're in effect at the bottom. You are pulling 1G. So what you're experiencing right now, if you look at Fc plus Fg, there's no centripetal force. You guys are just experiencing the normal pull of gravity. Now, this would be cool. Imagine that I could take my room and I could put it on a huge pendulum. And I'm going to start to swing my room back and forth and back and forth. So when you all hit the bottom of that arc, what's going to happen? What are you going to feel?
Heavy.
You're going to feel heavy because your body wants to move in a straight line. Now, what they're going to do at the top, you have force total equals Fc minus Fg. So that force total part is going to be a multiple of your normal gravitational acceleration. So they're going to go through different planets, orbital or gravitational bodies. The first one they're going to do is Moon's gravity. No, they're going to do Mars gravity, which is 1/3. So if you look at force total equals Fc minus Fg, they're going to set that force total equal to 1/3 Fg. So they're going to have 1/3 Fg equals Fc minus Fg. They're going to go to the moon. They're going to go, oh, that moon's gravity is 1/6. So they're going to have 1/6 Fg equals Fc minus Fg. Eventually, they're going to be in a state of weightlessness. So the total force is going to be
Zero.
0. So what that means is if you look at your force centripetal, then is what's being created by your gravitational field. So in a state of weightlessness over the top, and you can only experience this at the top because of the fact that you're subtracting values. You can't be weightless at the bottom. You can only feel heavy at the bottom, but you can experience a sense of weightlessness at the top. So this is why it's called the vomit comet, because you're going from, you typically get about 30 seconds of free fall at the top, and then you go down to the bottom of a parabolic curve, and then you're feeling really heavy, and then you're back to weightlessness, and then you're back to feeling heavy. So if you've seen the movie Apollo 13, and all those weightless scenes where they're floating around inside the spaceship, those are all filmed in 30-second increments inside a plane. And they would say, okay, 30 seconds, boom, y'all can float around and do that. And then they'd get to the bottom. So there was just day after day of filming these 30-second scenes where that's what allowed them to look like they were in space. Okay.
The effect that has on your body.
Once in the air, we climb up to 7,300 meters to start the first of 12 parabolas.
Here we go. This very first parabola is going to be Martian gravity, so 1/3 my body weight.
I can immediately feel myself detaching from the floor of the plane.
Strongman, 1 arm push-ups. Okay, lunar gravity.
2, 1, go. Just let your body float. Go up, enjoy with a few flags. Just feel your body completely relaxed in the air.
The parabolas are becoming increasingly severe. Basically, I'm skydiving inside the aircraft.
That is so strange. Oh, wow.
Go Team Silver! Woo-hoo!
This weightlessness thing is pretty cool. You only get short periods of time, maybe 20 seconds, 30 seconds at a time, but it's just like being in space.
We're all going to be facing that way, right? You're going to kneel, and you're going to try to crawl as fast as you can, okay? Okay? All right, very hot.
Yeah, sure, okay.
Go! Woo!
I can now better understand how difficult it must be to relearn every physical task during a prolonged spaceflight.
Okay. That is just the most unbelievable experience.
We're now completely weightless, able to fly like Superman. The constant pitching of the aircraft is pretty intense, and by parabola 10, the effects are starting to hit me.
Okay. Now,
He
we
died.
look at what happens in an extreme case. So this is what happens in fire.
Hi, I'm Steve Beatty with the Atlanta Journal-Constitution. I'm about to go for a ride with one of
So Blue Angels typically, when they're in town, will sacrifice a reporter to go up and fly with them. So, you know, the Blue Angels pilots, they're well trained, they're used to these large G-loads. So what you're going to see is the effects on a human body if you're not used to large G-loads.
Blue Angels. Push the bottles up to military power. There it is, here comes the burners. Oh yeah, there they are. Oh yeah. 100 knots. 120. 130, we're smoothly going to start rotating the aircraft. Ready? Line it up off the ground. We are airborne. Gear and flaps are coming. There's 220 knots. All right. 230. 260. 280. Are you ready? I am ready. Ready. Hit it.
Watch how fast.
Up we go. Oh, that's beautiful. Woo. You're ready for a big pull? We're going to do an implement. That's the inlet. You're back with me, Steve. Can you hear me? Yes, I am. Sorry.
Okay. What? This went nowhere. So here's what happens, is that your blood, oddly enough, has mass.
What?
And
I thought I just had void inside me. Void.
we'll use a penguin. Okay? So, imagine this is the penguin pilot. So when they're at the bottom of that curve, right? And this is why he said flex the muscles in your legs and in your stomach. So when you're at the bottom of that curve, your blood wants to keep going in a straight line. Unfortunately, as it goes in a straight line, that's away from your head, okay? And so the brain, basically, you lose so much oxygen and so much blood that your brain basically goes like a computer, goes into safe mode. It just shuts down. And so that's why for about 10, 15 seconds, that guy had no consciousness because of the fact that his brain had lost so much blood. So what they were trying to get him to do was flex the muscles in his stomach and his legs. If you flex those muscles, that makes it more difficult for that blood to flow down into your lower extremities. So fighter pilots will have what they call G-suits. So what happens with those is that there's bladders, or there's inflatable bladders around their stomach, around their legs. So that and there's an accelerometer in the plane. And so when they sense those large G's, those bladders will inflate and basically squeeze your body so that that blood can't flow down into your lower extremities. Now, Blue Angel pilots, those guys don't actually wear G-suits, mainly because of the fact they're constrictive, and those guys need to have full range of motion because they're flying such tight formations. So they go through extensive physical training so that when they do subject themselves to these loads, they don't pass out, because that would be bad.
We're doing a barrel roll. We're gonna touch cockpits together, and one of them
It
just
is
blacked
impressive.
out.
I don't think you.
No problem. Wow. I went nowhere there for a while. Yeah, I took a little bit of a nap. That's all right. That happens in the implement quite frequently. Wow. All right, 450 knots. Looking for obstructions. Aircraft looking good. Here we go. Take a deep breath. Watch your legs. Here's the burners. Here we go. Get back with me. Can you hear me, Steve? Yes. All right, you're back with me.
Okay,
What happens the third time?
same thing. Nothing new under the sun. He just passes out again. So, that's, but yeah, that's
Someone
what
tried to do
happened.
that recently. They threw up 17 times or passed out 4 different times. It's crazy.
I saw a clip of some like 80-something-year-old like
Yeah.
pilot or something that went up in one. It was completely fine.
Yeah.
He went all the time. He was still like they ran a side by side of like a new jet like
Pilot.
trainee going under the same G's, and he like blacks out, and the 86-year-old guy's eyes they like light up, and he's like, like the other guy's just like. And he's just like, you see all the snacks just go, but he's just like,
It's just gonna say Gershon Higher wants to connect to your display.
Wait, have you been to Dave and Buster's?
yeah.
There's this one
You can
the,
show
like
your
VR simulation that's like
clips.
$5, and one of those Top Gun where you're like in the jet, right?
Mm-hmm.
You don't necessarily feel those G's, but because you're blinded to.
Okay, so let's say that you're tasked with doing the calculations of saying, all right, let's say you want
This
Martian
roller coaster
gravity,
should not be.
where you feel 1/3 your weight. So what's gonna happen, the only variable that you can manipulate on this whole equation is what you want to experience when you're at the top. So if you want Martian gravity, you would set that equal to 1/3 Fg equals Fc minus Fg. Now at this point, can you combine any terms?
Yeah,
What can you end up with?
your FGs. What?
1/3 F.
4/3 FG. Right
4/3
there.
Fg, right?
Equals FC.
4/3, true?
Yeah.
So this is 4/3. Now, instead of Fg, I'm gonna put mg, because that's what you do, mass times gravitational acceleration, right? All I did was move this over. Now, in terms of centripetal force, I'm gonna write that as mv squared over r. So at this point, conveniently, what's gonna happen?
Your masses.
Mass cancels out. Now, if you solve for v, you're going to get 4/3, kind of the canine or dog's favorite equations, is 4/3 boom. So what that tells you is that if you want to figure out how fast you're going, you plug it into this equation. So if you want to look at, hey, I know the radius of this flight is going to be 4 kilometers, okay, whatever that is. Then that tells you what the speed of the plane has to be to create that value. If you want Martian, that's Martian. If you want lunar, the only thing that's going to change is that's going to be 1/6, okay? So then you'd have 1/6, you'd add that over, that would be 7/6, okay? Now, obviously there's a minimum velocity. So if I swing this thing around and I'm going fast enough, I complete the loop, right? So, but if I slow it down, I don't complete the loop. So there has to be some minimum velocity that I have to have for that rubber stopper to make it all the way around. And if I'm less than that, it's not going to do it. So to find that minimum velocity,
Set them equal to each other.
you say, all right, I'm going to set what I experience equal to 0, which is Fc minus Fg, right? Boom, I want to be in a state of weightlessness. So if my centripetal force is bigger than my gravitational force, this becomes a positive number and I complete the inside loop. At a minimum, I'm going to be in a state of weightlessness. So what that means is that, and hopefully this makes sense, oh, your gravitational force is what's creating the centripetal force. So this is what happens when we get into orbits. Well, so when you see something that's in orbit, it's because the gravitational force is providing just the same amount of centripetal force to keep you in orbit. So now we're going to do the same trick. We're going to go mg equaling mv squared over r. Again, what's going to happen to the masses?
Cancel.
And you get v equals the square root of GER. So here's how this plays out. So let me go to the lights back on. Wish my lights were on. Space here. Okay. So I've got a cup full of water. Okay? And so I'm going to take this thing and I'm going to swing this thing around. Okay? So what I want to calculate is the minimum velocity that I have to have for this thing to stay on there and complete a loop. So what's the only number that I need besides my gravitational acceleration?
Radius.
Radius. So roughly, what's the radius from the center pivot of my arm down to that cup?
2 meters.
Oh, it's not, there's no way, it's 2 meters.
1.5.
I'll call it 1.5. I can do 1.5. Okay,
Please don't hit that against the ceiling. That'd be,
I'm going to try not to.
That would
Okay.
be funny.
So
Water. And
here's my arm. There's my hand, there's the waiter, there's the cup of water.
I
We
see how it
said
is.
that's about 1.5 meters.
Draw yourself buff, do you?
Huh?
I said, draw yourself buff, do you?
Thick forearm and bicep.
You have to be drawing it.
Oh man. Those are some
Okay.
rough biceps and triceps.
Realistically, it's more like this.
Eh,
So,
I like that
Gapshon. So take the square root of G times 1.5 meters. And the square root.
3.83.
Okay, so at a minimum, that has to be traveling 3.83 meters per second to stay on there. Okay? So, try this. Try not to hit the ceiling. Right?
I'll do it less.
So,
Slow down a little bit.
nope. Nope. So, here's the story. So, if you look at what's happening up at the top, here, let's start with this idea. So when you view this thing when it's at the top, because I'm not worried about at the bottom, I'm worried about at the top. Okay? So this thing is going around like this. Is there a force pushing the cup up against the platform? And that's why it stays there.
No.
Why not? Your
Yeah,
answer is
it's
right.
Or no, it's inertia, not an inertia isn't a force.
Inertia is not a force. Does the cup want to travel in a straight line?
Yeah.
Yes.
Yes. So basically that platform is preventing that from happening. Okay? So when that's going fast enough, the centripetal force that you need, some of that's being provided by gravity. So what would happen is that imagine that I could outfit a little scale inside that platform. So if that thing's going fast enough, what that scale would read is the difference between the centripetal force that you need and what's being provided by gravity. Now, if I did that in a zero gravity field, the reading on that scale would just be the centripetal force, okay? Because there would be no gravity to help it out. But because of the fact that there is a gravitational field, then that's providing some of that force. So that's why I was able to stay dry as I went around. Okay, so stop that camera, unplug it, let's go back to the roller coaster for a second.